On to section 12.4, where we're going to analyze this. Here we want to identify forces that are exerted on a simple pendulum or any sort of pendulum, and use the small angle approximation to model a pendulum as simple harmonic motion, to be able to then solve problems involving angular frequency and period of a pendulum. So a simple pendulum is really just a system, another one that exhibits the periodic motion, much like a block on a spring. Here you have some sort of mass that is suspended by a light string or rod of length L and pulled it away at some angle theta. The upper end is fixed, and the size of the pendulum or the bob is small compared to the length L of the string or the rod. This would be what we call a simple pendulum when that is true, and it really just sort of models the particle model. Now, this would oscillate about its lowest position, which would then be considered the equilibrium position down here. So what forces would act on this pendulum bob? Well, of course, you would have the tension in the string pulling it up this way and gravity trying to pull it down. Now, notice that this gravity component here would actually have pieces that are both along the lines of the tension and tangential to the tension. So if we were to set up an axis that looked like this, we would find that we have really this would be our angle theta in here that would match this angle theta here. And as we break this down, we'd find that the piece tangent to the motion here would be like an mg sine of theta, and this piece here that would be opposite the tension would be like an mg cosine of theta. Now, as we look at the tangential component of mg, this component here, if we really wanted to define the direction that it acted, we see it acting this way here, but if we went over to this side, it would be acting this way. So really what we could say is that it's always acting towards the equilibrium position, towards theta equals 0, which ultimately means that gravity is going to act as a restoring force. So this mg sine of theta could be set equal to ma, where a is again the second derivative of the position. And position here is going to be defined as an arc length. Remember, arc length is equal to the radius times that angle theta. In this case, the radius would be the length of the string. Now, to simplify that a little bit, we could cancel out the m's, and we could also rewrite s as, again, an L theta. So L could come outside of the differential that we have there, and we could write this as L times the second derivative of theta with respect to t, and that'd be equal to a negative g sine of theta. Now, at this point, we could move the L over, and we come up with this expression here. What we need to remember is that for simple harmonic motion, the definition that we had for that was that the second derivative of a function had to be equal to a constant times that exact same function. Is that the case here? The answer is not quite. The second derivative of the function theta is equal to some constant, but it's a constant not times theta, but instead a constant times the sine of theta. Here's where we're going to bring in the small angle approximation. Now, the small angle approximation basically says that the sine of an angle is about equal to the value of the angle itself when theta is measured in radians. And that is true up to about 0.2 radians or 10 degrees. What you can see on this graph here is that they show you a graph of x and in red, and also a graph of the sine of x in green. And what you notice is that through about 0.2 radians, that these graphs completely line up and overlap. It is when the angles get larger that the graphs begin to diverge, and the value of the angle itself is no longer so much equal to the sine of the angle. So if we stick with small angles, then we could rewrite that expression from the last slide as this, where we do have the second derivative of theta being equal to some constant times that same function theta. And if that's the case, we can then fit it to our simple harmonic motion equation, where theta would be equal to some theta max times the cosine of omega t plus phi. Now, theta max would be your maximum angular position, much like the capital A or the amplitude. Now we're saying that that's the same thing as like a theta max here. In this case, omega would be equal to the square root of g over L, and period is of course still a 2 pi over omega, but since omega is square root of g over L, we could now write the period as 2 pi times the square root of L over g. Now notice that the period of this oscillator, so if we think about a pendulum that swings back and forth, and the period of that motion and going back and forth, notice that that period is really just dependent on the length of the pendulum and the value of g in that given location. So for these small angles, the period only depends on length and gravity, basically the free fall acceleration. Now, since that period is independent of the mass and m doesn't show up in there anywhere, that means that all simple pendulums of some length L will oscillate with the exact same period. It doesn't matter what size for the bob that you stick on there, they will have the same oscillation period. So let's try a problem together. Let's say that a man goes into a very tall tower and he needs to find the height of this tower. Now, of course, since we are working in our perfect physics world, he is so lucky as to find a pendulum that is hanging from the ceiling of the tower down to almost the floor. And as that pendulum swings back and forth, he notices that the period of the pendulum is equal to 12 seconds. How tall is this tower? Well, again, we just saw on the last slide the equation for the period of a pendulum. Remember, period is equal to 2 pi over omega, or for a pendulum then, a simple pendulum, 2 pi times the square root of L over g. Now, this problem is simple in that we can simply plug in the period of our pendulum, the 2 pi. The length of the pendulum would now be what we're looking for because the length of the pendulum does in fact represent the height of the tower. And g is on Earth, so 9.8. Go ahead and take a second, pause the video, and try to solve this equation yourself. You'd find that L, or the height of the tower, is about 35.7 meters. When we come back to class, we'll try some more of these problems.